Go.
Hello, welcome to the Academy. And this is a video, first video on a series of Calculus 3 lessons. And the first topic is going to be a review of vectors. And so, first of all, I want to talk about what is a vector. And we've seen some of these, and there are several ways of expressing them. The first concept is the geometric idea of a vector. So basically, a Euclidean vector is an arrow. It looks something like this, from point A to point B, for example. We'll call this vector AB. And the property of a vector is it has a defined length and it has a direction. So it's from A to B, not B to A, for example. And it's pointing that way. But vectors can also be described in another way, based on components. So if we have a vector over here, so I have this vector, what I can do is if I set up a coordinate system, let's say x and y, Cartesian coordinates, and then I can describe this vector based on the length in each of the two coordinate directions. So I can say this is the x component, and this is the y component, where x is measured positively this way and negative this way. And so then I can talk about this vector, say vector v, as v equals x comma y. So if I have a vector, for example, one that looks something like this, it goes out 3 here and 4 there, this is the vector 3, 4. And it doesn't matter if it's here, of course. I can just copy the same vector here, 3, 4, it's still going to be the same vector. It doesn't matter where it is on the actual coordinate plane. It's still 3 and 4 because it goes 3 horizontally and 4 vertically. And this also allows us to talk about vectors in a slightly different way. For example, this 3, 4 can also be written because it only needs the components of the x and y, or x, y, and z if you want to do 3-dimensional. You can have it as a single row of numbers or as a matrix with one dimension. So it's x and y. Or you can have it as a row vector, x, y. But more commonly, we see the matrix like this, and you have x, y, z. Like that. So next time we want to talk about some operations that you can do with vectors. First is addition. And when you add a vector, for example, add vector A and vector B, to add them, you connect A and B like this. So it's called a tip to tail, because the tip of this vector connects to the tail, I guess, of this other vector. So then you have a new vector by connecting this starting point of A to the end point of B is this A plus B. So how do we understand this in terms of the components? Well, if you have two vectors being added in this way, to create a new vector, what you do, you can see that the x component of this new vector will be the x component of the first vector, x1, added to the x component of the second vector, x2, which is this length, same as this length. And so you just add the x components, and similarly you can see the y components being added, y1 and y2. And of course, from our matrix definition, this seems pretty clear. x1, y1 plus x2, y2 will just give you a new matrix or a new vector, x1 plus x2 and y1 plus y2. And this just follows from basic matrix addition rules as well. And so to add vectors, you simply add their components. And subtraction is pretty similar. Basically, when you have a negative vector, is the vector that goes the other way. So this is a vector A, this is negative A. So when you subtract, it's the same thing, you just subtract the components. Or geometrically, you can think of A, and this is B, minus B would be like that. And so it would be minus B would be here, and then you get your new vector A minus B. And you do the same thing for these, you just subtract the components. Another thing you can do with vectors is you can multiply them. But you multiply them by a scalar, which is a regular number, like 5 or 12. And how you do that is pretty simple. Basically, if this is a vector A, then 2A, you just have twice the length. 2A. And similarly, 3A, 4A, half of A would be half the length. And negative A, like I said before, just going in the opposite direction. And again, this makes sense when you look at the components just get multiplied. If you have a number like 2 times your vector xy, it's going to be 2x and 2y. Again, from matrix rules. And so if I have a vector, let's take the first example we had, which had 3 here and 4 there, 3, 4. You can multiply this by any number, like 7, and just get 21 and 28. That would be a new vector. So 7 times that vector is this new vector. Now multiplying vectors by each other is a slightly different idea. So we have to think about it a little more carefully because there's several ways to do it. The first one is called dot product. When you take the dot product of 2 vectors, this is sometimes also called a scalar product because it creates a regular number. And so if I have a vector A and a vector B, the dot product, you write it like this, A dot B, a little dot in between. So this result, there are a couple of ways of finding it. One way is to think about it is A times B in the direction of A, or A in the direction of B times B. So basically, you can find out how much A is in the B direction and then multiply them together. Or if you think about this as an angle between the vectors theta, then this would be, or I take the absolute value or length, this represents the length of A. Of vector A. Also could be like this, with two lines. So it doesn't look like the absolute value. But, so we have this times the cosine of the angle. You get A in the direction of B. Then you multiply that by B. And that is one way of thinking about the dot product. Or rewritten like this. The lengths times the cosine of the angle between them. Another way of doing it is, let's say A is x1, y1, and B is x2, y2, then the dot product is x1, x2 plus y1, y2. So you multiply these components and you get the answer. Now, these two are the same thing, and we can show that that's the case. Here's a quick proof. Okay, so if we start with this definition over here. So A dot B x1, x2 plus y1, y2, we can find that, well, first let's express A and B draw the x and y axes. We can see, actually let me redraw it over here. This is A, this is B, and each one of them has their own angle. Let's call this, I don't know, phi, and this angle over here, we can call it phi1. And now we can express the x and the y components of A and B in terms of the angle and the length. So the length of A is the magnitude of A. And the same thing, the length here is the magnitude of B. Then we can talk about A being A times the cosine of phi1, comma, the length of A times the sine. And that would be the y component, and this is the x component. And similarly for B, B cosine of the angle, and B sine of the angle. So this is x1, x2, and y1, it's x1, y1, x2, y2. And so when we rewrite this like this, we say that A dot product of B is plus this times this, so that's A times B times cosine phi1 plus A B sine phi1. Now we can factor out this magnitude of A times magnitude of B. And we just get this cosine B cosine phi1 plus sine phi1. Now this over here, if you remember or if you know the cosine angle sum formula, there's a sum of an angle, for example, a plus b, a plus or minus b, will give you cosine a cosine b minus plus sine a sine b. So if it's plus, then it will be minus. If it's minus, then it will be plus. But since we have a plus over here, this is a plus, so we're going to use the plus here, which corresponds to the minus sign here. And so this whole thing is really, can be simplified into cosine of the difference of the angles, phi1 minus phi, and if you subtract the two angles, you just get what's left in between is the angle between them, theta. So this is just a the cosine theta. And that's the proof of that. And so that is the dot product, pretty much. Another way of thinking about it, if you want, another way is A transpose B, if you want the matrix form. So if A is x1, y1, transposing the matrix, this will become, turn the row into a column and vice versa, x1, y1. Then if you multiply by B, which is still going to be a column, now the dimensions will work out. So when you multiply matrices like this, you'll get x1, x2 plus y1, y2, which is what we said over here. So that's the dot product. But there's another product that is called the cross product. And it has a sort of an x multiplication sign. And this gives you, instead of giving you a number, like this one did, it'll give you another vector. And this vector, it's kind of hard to express, but basically it only works for 3 dimensions and also 7 dimensions, but most of it working in 3 dimensions. What it does is have a vector A and B. Okay, a new vector perpendicular to both of the vectors, so perpendicular to the plane that the vectors are in. So it will be pointing outwards or inwards, depending on the orientation. And the length of this, so the length of this new vector will be length of A, length of B, sine theta, the angle between them. And the direction is determined by the right-hand rule. Which says, basically, if you take your right hand and the order that you read it in, A is your index finger and B is your middle finger, then the new vector, C, I guess, will be pointing in the direction of your thumb. So in this case, A and B, A cross B, will be pointing into the board and will have this length. And there are ways to calculate that using the components. But first I want to talk about take a side note here, a little bit of digression. Talk a little more about unit vectors. So as I said, vectors have a length, a magnitude, and a direction. But a lot of times you want to take a vector and you want to shrink it down so you keep the same direction, but you want it to have length 1. So if you want the length to be 1, what you have to do is you have to find the length of your original vector and divide it by that new length. So basically, with a hat, which is usually used for unit vectors, will be a divided by its magnitude. And as an example, let's see the one that we did previously, the vector 3, 4. So 3, 4 clearly does not have length 1. But we can find a vector in this direction that is a unit vector by finding the length. Now, to find the length of the vector, you just have to think about the Pythagorean theorem. This is 3 and this is 4. What you just do is you just say the length squared equals 3 squared plus 4 squared, or in general, x squared plus y squared. And so the length is square root of that. Or in this case, square root of 3 squared plus 4 squared, which is 5. And so if we want to find the unit vector, you just divide it by 5, divided by its length, and you get 3/5, 4/5. And this allows us to talk about vectors in one more way, using what we call the unit vectors in each of the coordinate directions. Generally, the convention is I is this vector right here, the unit vector in the x direction, which is x-axis. J is the y direction. And k would be, I guess, in the z direction, coming out like this. And that would be coming out of the board. Just want to visualize that like that. And then these are all unit vectors, so they'll have length 1. And so now you can think about a vector like 3 and 4, 3, 4, as the vector 3i, that would be 3, a length 3 here, and a length 4 here, 4j. Then you just add the two together, so you could have 3i plus 4j. And that's another way of writing this vector. And if you had a z component, you would add some number times k, which is the z direction. So back to this, now, if we want to calculate the cross product, you have to use these I, j, and k, at least. This is the easiest way to calculate it. So if A is x1, y1, z1, and B is x2, y2, z2, then you find the determinant of this matrix ijk, x1, y1, z1, and x2, y2, z2. And find the determinant, you multiply these diagonals. So you just sort of basically rewrite these two rows. So you multiply the main diagonals and add them together. So that would be y1 z2 I plus z1 x2 j plus x1 y2 k, and minus the off diagonals. So that would be x2 y1 k plus y2 z1 I plus z2 x1j. This is a very long formula, and you could group the terms together, so it would be y1 z2 minus y2 z1 I, and then do the rest for all of them. But this way is a much simpler way of writing it. So now let's probably do some examples of cross product and dot product. Just to get used to them. So let's say A is the vector 1, 3, and B is the vector 7, negative 2, and A dot product with B would be, what would we do first? We're going to multiply the x components together, so 1 times 7, then plus 3 times negative 2. So we use 7 plus negative 6, which is 1. So the dot product of these two would just be 1. But if you want to take a cross product, we have to rewrite these as 1, 3, 0. Because we can only do this in 3 dimensions. So what we do is use the formula from over there, ijk, 1, 3, 0, 7, negative 2, 0. And this would be 3 times 0 is 0, so 0i. 0 times 7 is 0, 0j. Then negative 2k minus, what is this, 21k, and the other ones will also be 0, so it's just plus 0. So zeros, you just forget about them. So it's really negative 2 minus 21, it's negative 23k. And now, how does this correspond to what we said before about the cross product? This should be what we expect because we said these are only in the x and y direction, which means they're in this plane. So if we draw a quick sketch, 1, 3 will look something like this, and 7, negative 2, something like this. And the cross product must be perpendicular to them both, so it must be going in the z direction, but A cross B by the right hand rule is going to be pointing into the board, so it's going to be pointing down in the negative direction, so that's why it's negative 23k. So that makes sense. Okay, so finally let's talk a little bit about where we use vectors on applications. Especially in physics, a lot of times you want to have quantities that have both a length or a magnitude and a direction. For example, velocity vector v, which tells you how fast you're going and in what direction. And so, if you actually find the length of this, that would be speed. Another one is force. F Now F equals ma is also an equation. In physics, force equals mass times acceleration vector. And we can also talk about position as a vector as well. For example, a vector r can tell you where something is based on a coordinate system. So if there's a point over here, x, y, x comma y, you can say this corresponds to the vector xy, or xi plus yj, whichever way. They're all equivalent ways, really. And one more thing that's useful that you can do with vectors is find normality or perpendicular things because of this equation right here. So if I have two vectors that are at right angles to each other, this is 90 degrees, or 2 radians, and the dot product of two vectors that are perpendicular, we know it's the cosine of the angle with the cosine of 90 degrees is 0. So this is just multiplying by 0. And so if you have two vectors and the dot product is 0, then you know that they must be perpendicular to each other. Or one of the vectors has 0 length. That's a 0 vector. But if you know that they're non-zero length, then you can find two things that are perpendicular, or orthogonal sometimes they're called. Just by taking the dot product, which you can do by multiplying the components, as we've shown over here. And then if it's equal to 0, then they're perpendicular to each other. I hope that was a good review of vectors. I'll see you next time.